Welcome to episode 347 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm okay, Rob. How are you doing?
I'm doing all right. Saw a movie last night. Saw The
You saw a movie
Northman.
last? Which one?
Yeah. Northman.
I think I've seen a preview for that.
It's pretty good. Very, very violent, but very good.
Is
So
it?
It's like Hamlet, but with Vikings.
Is it violent in like a comedic kind of
No,
way?
dramatic
Okay.
action movie. Yeah.
Okay. I say I don't go for over-the-top violence unless it's
Mhm.
over the top to the point of ridiculousness. So I'll watch like the Expendables movies, which are just comedy, basically. Like, yes, not that much blood can't come out of a human, like that kind of.
Yeah. You have anything you want to talk about before we get started?
Well, I mean, we feel like we may as well go ahead and mention that C++ on C registration is still open. And
Yes.
I will be doing a workshop there
Mm-hmm.
on doing code reviews because I thought that seemed like a fun one. I've never done a workshop on that before. But, I like doing code reviews. So I thought maybe if I can kind of help people get a better feel for what a good code review looks like, then that would be fun. And I'm keynoting at that, which I think we've mentioned. Have we mentioned that? Okay.
When is C++ on C?
4th of July
Summer?
weekend.
Oh, okay.
Yeah, it's like July 3rd, I think, is the first day with the workshops. I think that's right. And then 4, 5, 6, something like that. It's either the 4th through the 7th or the 3rd through the 6th.
Okay. We can put those dates in the show notes or put a link in. Yeah.
Yeah. But that's the next conference that I know that I'm going to, so that's exciting.
Very exciting. All right. Well, at the top of every episode, I like to read a piece of feedback. We got this direct message to the CppCast account a couple of weeks ago. This is from Jacob saying, "Hey guys, I really enjoyed the conversation about Zig with Andrew. The const expr stuff seems really great. In particular, const expr for sounds like it saves a lot of boilerplate compared to C++. I would also like to suggest a guest, Mark Hoemmen. He's had a long career in HPC and scientific computing. I think you could have an interesting conversation about those fields. In particular, two topics which I don't think have been discussed on the podcast, are Kokkos and the distributed algebra libraries Tpetra, where Mark was one of its main authors. And yeah, so we're actually going to be talking to Mark in just a moment. Thank you for the suggestion, Jacob.
Definitely.
Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Mark Hoemmen. Mark is a scientific software developer with a background in parallel computing and numerical linear algebra. He has a bachelor's degree in mathematics and computer science from the University of Illinois Urbana-Champaign and a PhD in computer science from the University of California, Berkeley. After finishing his studies, Mark worked at Sandia National Lab for 10 years. There, he contributed to two open source C++ software projects, Trillinos and Kokkos. For the last 2 years at Sandia, he focused more on applying Trillinos and Kokkos to non-open source engineering, like including simulation applications. In early 2020, he moved to Stellar Science, a scientific software company based in Albuquerque, and contributed to several non-open source physics and discrete event simulations. This April, Mark joined the Dev Tech Compute team at NVIDIA, working remotely from his home in Albuquerque, New Mexico. Mark's preferred programming language is C++. He has been writing it professionally for 22 years and has been contributing to the C++ standard process for the last 5. He is co-author on 3 standards library proposals: In Flight, P1673, C++ BLAS interface, P009, MDspan, and P1684 MDarray. After C++, he feels most comfortable working in Python and can get by in Fortran, MATLAB, and ANSI Common Lisp. In his spare time, he likes to play mandolin, lute, and Baroque guitar. Mark, welcome to the show.
Hi, thank you so much. I didn't realize you were going to be reading the entire thing out loud, or else I would have shortened it more. Sorry.
No problem.
Oh, we just had a guest on who is also from Urbana, right? They were a like adjunct professor or something like that.
Sounds familiar. I know we've had a lot of National Lab developers over the past few years.
No, I mean
too.
Illinois
Yeah.
from the
I know.
yeah. And yeah, I don't know. Anyhow, Albuquerque though, the most difficult to spell capital city in America, I think. No, it's not a capital. Most difficult to spell large city in America, I think.
Well, what's funnier is that the Albuquerque in Spain has an extra R.
Oh, does
We
it really?
dropped it. Yeah, we dropped it at some point.
Where do you stick an extra R in there?
Burque.
That's fun. Okay.
It supposedly stands for the cork oak, the oak tree from which you harvest cork.
Oh.
Which in Spain is what they do there, in that part of Spain.
I did not have any idea about that whatsoever.
Yeah.
I just can't hear the name without starting to sing in the back of my head Weird Al's Albuquerque song.
Yes.
All right. Well, Mark, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about your involvement with linear algebra libraries, okay?
Sure.
Okay, so this first one is what's new for C++ debugging in VS Code. And, this seems like it's a pretty good update. They now support debugging on the Apple M1 chip. They support data breakpoints with GDB, which is one of my favorite features in normal Visual Studio. Being able to set data breakpoints is really handy. So really nice that they're bringing that to GDB in VS Code. And they also have a quick run or debug play button. So if you just make a single C++ file, which apparently is pretty common with VS Code, you can just hit play without having to set up all of the other project settings and everything to get it compiling.
Nice.
Yeah, really nice.
And just add edit and continue features, and it will be a full Visual Studio replacement product at this point.
Pretty much.
I need to spend a little bit more time with VS Code. It's worked well, actually. I've tried it with C++ projects a few times recently. And for certain applications, I actually prefer it over Visual Studio at this point.
Yeah, I still haven't really used it for like real projects, but it's my go-to editor if I just want to view something or work on a script or something like that, but I don't use it for larger projects.
Live preview of Markdown.
Yeah, that's nice.
I have been using that feature quite extensively with my proposal work. It's a great Markdown editor. So that's mainly what I use it for. But it's nice to pull up a little code example or something. For the last 2 years at my last job, we did Visual Studio development. So, but code was useful for Markdown.
Yeah,
definitely. All right. Next thing we have is a post from Janheed Manid's blog, and this is conformance should mean something, fputc, and freestanding. I apologize. I forgot how long this article was when I first grabbed the link, and I did not give myself enough time to read it. So I'm hoping, Jason and Mark, you can talk me through this one.
We're gonna have to edit this bit out because I forgot to read this article also.
Oh no. Mark, did you read it?
I did.
Okay.
I've been very fortunate, blessed perhaps, not to have to deal with very strange implementations of C.
Mm-hmm.
Okay.
And so the concern here is a little foreign to me, but when I read it, it's sort of like one of those slow creeping horror novels where you discover something unnatural lurks beneath the surface.
And it has to do with freestanding implementation, so no operating system?
No, it's worse than that. It's somehow even worse than that. It's like the meaning of the word character is not 100% clear in the standard, and some implementations apparently exploit that.
Oh, that's handy.
Yeah.
I don't know, you reach a point where you've read too many of Janheed's articles, and you wonder if any of this is meaningful at all.
Yeah, you start to question the meaning of words. It's a very frightening thing. You shouldn't do this for too long, or your sanity is. You have to buff your sanity before you do this.
I've always been just a little bothered by the fact that all of the characters, the C standard library character functions take int. That's always bothered me. Like, there was an 8-bit type. There was characters always been in the C standard, right? Because that was one of the main points, was that the developers of C wanted to be able to do byte addressing on hardware that supported it, and previous languages didn't support that. So why the heck did they make those functions take an int instead of a char? Troubles me. Anyhow.
Okay. And then this last thing we have is a YouTube video, and this is Stefan Lauwe at STL from the MSVC team talking about MSVC's C++ 20 and 23 compiler and library updates. And I believe this video is part of the virtual C++.
It was
Sure, virtual conference that's going on right now. So it's good to see plenty of updates to go over. So always great to see all the compilers chugging on ahead with the new releases.
And I think it definitely worth commenting is that some of the C++ 20 conformance fixes that are going into Visual Studio 2022 are being backported into Visual Studio 2019 in an upcoming release.
Yeah, some of them are just important enough, worth backporting into 2019 that he commented on.
Yeah, having worked at a defense contractor for the last 2 years, their world is a little bit more Windowsy and a little bit more concerned about ABI compatibility than the HPC world. And so that was kind of an eye-opener for me to realize before that was never a concern that, oh, whatever, you break ABI, whatever, you recompile everything anyway, whatever. But I start to see the importance of that in the last 2 years.
Fascinating. So that might make you only the second guest that we've had on in the last 2 years, actually, who says that ABI compatibility, is important. So that's an aside at the moment, but whatever, we have an interview to do here. Do you, from an ABI perspective, do you do things to make sure that the libraries you produce are still ABI compatible with previous versions?
Yes, in my last project, one of the things that we designed was a profiling system. So something that developers could use to measure the performance of chunks of C++ code, something that would work in a thread parallel world and not have too much performance overhead. And the system works by loading from a dynamic shared library, loading from a DLL. And so there, the ABI matters. And so we put a lot of thought into making sure that the ABI was really a C ABI. So we wouldn't have, that C89 subset of C where the ABI generally is pretty stable.
Wow.
And having a versioning system. But it always shocks me how people casually expect C++ ABI to be stable.
Yeah. No,
but they do. Yeah.
So what is it? Were we talking like an interface that's nothing but like void pointers and ints or something like that? If you want to be like that far back?
It was like that. It was, we did rely on the C student type aliases. So the, int 32T and int 64T and void star and character star for our character arrays. I mean, ABI can go to the extremes. When I've worked in distributed memory parallel code with the message passing interface with MPI, there are MPI backends that will do ABI translation of data. Like they'll flip the endianness of doubles. And you pay for that, but there are implementations that could do that. And so this wasn't going to that extreme. It was assuming that your endianness won't differ and the bit layout of things isn't going to change.
Did you have to ever approach situations where you said, well, for technical reasons, we really do need to break ABI here. Now, what do we do? Did that ever come up on that project?
That did come up on that project, and the way that we handled it was versioning. So there was always a stable interface that would let you query the version that the library provides.
Okay.
And so there was a kind of a dialogue. The application says, well, I expect this version or this range of versions, and the library says, well, I provide this range of versions, and if they don't meet, then the application knows to bail or not load the library. Profiling is best effort, and so users might still want to run even if they don't have profiling. What they don't want is the application crashes in the middle because it called a hook that doesn't exist or has a different signature. That would be uncool.
Did you ever have to revert to anything like function EX version 2?
Thankfully, no. Because it's profiling, the kinds of things you want to profile. But that actually was very interesting because this was a discrete event simulator, and so it was like a serious video game,
right?
And where things happen and simulated events happen and simulated entities interact with each other, kind of a wargaming thing.
Okay.
Oh, okay.
And so the goal was to run all of this in a thread parallel context. And so it was a little bit different than, say, the Kokkos world or the high performance computing world, where you know where your thread parallel loops are and you profile around them. And in this last project, I was profiling inside of thread parallel code. And so I had to design the profiling interface and the profiling system differently to accommodate the fact that it's always running in a thread parallel world. And that even meant different interfaces that were meant to work in a thread parallel world, but also hopefully that didn't have stumbling blocks for users.
So, I'm curious, trying to do runtime profiling with an ABI hook and a thread parallel world, like how much performance impact would you cause by trying to measure the performance of things?
That was an important question for us. It turns out if you don't load the hooks, the performance impact is I test a null function pointer, and then I do nothing. And so if I assume that the interface is inlined, if I don't consider a little scope guard creation kind of thing, then I'm testing on scope guard creation. I test if the function pointer is null, and on scope guard destruction, I test if a function pointer is null.
Okay.
And so the kinds of things you would want to measure performance of need to be significantly bigger than measuring a function pointer. But yeah, you have to think of the locality issues, right? If you're not in, you're kind of reaching outside of your iCache maybe if you do that. So we weren't really thinking of that fine-grained. It should be coarse enough grained that you don't worry about that.
Right. So it's not like a tight loop where you're creating one of these things, your scope guard inside of, okay. Sometimes when I look at problems like that, I wonder like, well, how much branch prediction cache pressure am I putting on, because now I've got this extra check here and this check here, and like, what, because then sometimes we've had previous guests on that have these stories that are like, well, on Tuesday the code always ran faster, and it comes down to something completely random because on Tuesday the timestamp caused a different pressure on some branch prediction unit or whatever, like so anyhow.
Yeah, that's a thing to think about. And we were trying to design for the future, but this was an old code base, and having something that could measure performance was better than having nothing, which is what they had at the time. But especially for measuring profiling, I had to fight really hard about overheads because I was assuming that I didn't want threads to synchronize, and I wanted minimal synchronization when I measured performance of things, and sometimes the users or the project leaders didn't really understand.
So it all had to be thread safe, but I'm guessing mostly lock free, because otherwise, yeah.
Yes. Well, there was like how much do you? Yeah, there are lots of questions there.
Right.
Yeah.
Interesting.
All right. Well, Mark, you heard me introduce your, the listener comment suggesting we have you on. But before having you on the show, you mentioned how you're not actively working on these libraries anymore. But could you maybe start off by giving us a little bit of background on what Kokkos and Tpetra are and your involvement with them? Okay.
Yeah. So I'll start with Tpetra because that came first in time, sort of. There's a bit of a history there. So Indian National Laboratories, as part of their work, needs to simulate things, physics things, engineering things. For example, if you drop something on your toe, you want to know if it goes boom or not. That's sort of the coarse way of describing it. And a lot of what Sandia is concerned about is safety, and for their catchphrase is always never, and that means it always goes boom when you want it to, and it never goes boom when you don't.
That sounds important for the kind of research that's done in New Mexico.
Yes, it's very important, and I live here too, so it matters to me. And a lot of what I was concerned with was the never part of that. So in engineering situations, in situations where people are doing work, where people are building things or taking things apart, they want to know if it's safe, or if an accident happens, will something incredibly bad happen, or will something not so bad happen? And so a lot of my work was supporting simulations to do that. And these were physics simulations, so things were crashing into other things, or things were on fire and crashing into other things. So that was a thing. Yeah, things sometimes catch on fire because they crash into other things. And so that involves finite element, finite volume, turning the continuous real world into discrete little chunks of things and approximating physics that way. And so you get from physics equations that describe the real world to a discrete version of them that you could maybe solve on a computer. And then you go from that to maybe a linear system or a least squares problem, a math problem that's something that I can help you solve. And so my main concern at Sandia, I did work some on the discretizations, but my main concern was once you've turned the physics into a math problem, a matrix kind of problem, a linear algebra problem, then I worked on libraries to help you solve that fast and correctly. And so Trilinos is a massive library of things to help you solve math problems efficiently and correctly. And Tpetra was kind of the center of that, the sparse matrices and vectors, parallel data structures, to help you do that in an efficient way.
Okay.
And so I was concerned with interfaces, I was concerned with implementations. When I started working on Tpetra, that was about the end of 2010. At the time, it had been, it was the template version of ePetra, Essential Petra. E stands for essential.
Okay.
Historically, in the 2000s, the national labs, like the idea of using C++ was new for our kind of work. And so vendors of supercomputer systems didn't necessarily try to support the latest C++ versions, or
What
their
were
interest
you
in
like using before? C or MATLAB or something?
Fortran.
Fortran?
Fortran, yeah, or C. There's a little bit of history of parallel computing there. So everything was kind of Fortran for a long time, with a little occasional experimentation with other languages. That was the sort of Cray 1 vector supercomputing world. Fortran with pragmas. And as parallel computers started to diverge in architectures in the 80s, there were distributed memory parallel computers. Sandia was an early adopter, one of the early adopters of those technologies. And those tended to use C as their native programming language. And so people started to implement C versions of these libraries. And then it was really like 2000 and after when C++ started to pick up in the big national lab world. And so compiler support circa 2004 was still a little bit weak.
Right.
And later on, and so people had to say, oh yeah, we can't use templates, or we got to not use this feature or that feature. And so eventually the compilers caught up, and people wanted to use generic libraries, and they wanted to use more of C++. And that's where Tpetra came in. It was a postdoc project in 2009. So a postdoc worked on it for a year, maybe 2 years, and then he left for a different lab. And then what they wanted to use Tpetra for was, they wanted to solve very large problems where you couldn't express the dimensions of the matrix in a 32-bit integer.
But
so
you can't express the dimensions in a 32-bit integer.
The number of rows or the number of columns. So
that is
matrices,
a very large problem.
Yeah, but people want to solve problems with more than 4 billion degrees of freedom. That was a thing. And people have solved linear systems with hundreds of billions of degrees of freedom. That's a thing that people do. It's not a regular thing that people do. Sometimes it's a little bit more of a stunt, but people solve real problems that are large. It's hard to wrap your head around running in parallel on 1 million processors and having problems that have billions of degrees of freedom. That's what people do.
You made a comment a moment ago that caught my attention. You said in the 90s when parallel computing architecture started to diverge. And I got my computer science degree in the 90s, and I do remember these conversations about, shared memory versus distributed memory versus, whatever, and how the interconnects work and whatever. I've gotten the gut impression that all of that conversation has mostly gone away. And today, all the supercomputers are effectively the same thing of a bunch of nodes of Linux boxes that are connected together with Ethernet. Am I missing something, or is that like...
It's kind of gone all the way around in the circle, as it tends to do.
Okay.
So it was really the 80s when distributed memory parallelism versus shared memory vector parallelism started to become a thing.
Okay.
But by the mid 2000s, the world that you describe, Linux boxes or Unix boxes connected over a network, that was kind of the world,
right?
Where people are programming in MPI, the message passing interface, in a distributed memory way across many nodes. And part of the reason they use MPI was because their problems are large and they don't fit in memory on a single node.
Okay.
But then with GPUs, with accelerators, the world starts to get more interesting again. And so now, yeah, we still have nodes connected together over a network to solve the biggest problems, but the nodes get more interesting, richer.
Okay.
So that's the world that we find ourselves in today.
Interesting. I also remember conversations about like, well, if we'd made really simple RISC machines and fit 1,000 cores on a CPU, that seems to have largely gone away in favor of GPU, which is less general.
What is a GPU?
It is, yes, but it's not what we had in our minds when we thought 1,000 cores on one chip.
But it is. That's what it is.
Right.
And a lot of other architectures that aren't called GPU have that design of many small, individually low power instruction units that work in parallel to solve your problem. Okay. And so that's modern computer architecture. This is perhaps a good segue to talk about Kokkos.
Go for it.
Let's go for it.
Thank you. So, so as was mentioned, in the 2000s, architecture kind of stabilized, and the way that you program nodes of Linux is that you use MPI, which is a distributed memory explicit message passing programming model. And Trilinos, Tpetra, those kinds of codes grew up in this world where we could rely on MPI being the way that you program.
Okay.
And so you don't think so much about how you program on a single node. You're writing straight line, single thread code, and you're communicating with other processes on other nodes. And so because the programming model was stable, people built up a huge software infrastructure to solve all kinds of problems. They built huge applications, millions and millions, tens of millions of lines of code, lines of C++. So like Trilinos is single-digit millions of lines of code to solve linear systems.
Wow.
And so that stability of programming model made it easy to write code and build up large systems. But as node architecture started to diverge again, it became harder to do that because do I write in CUDA? Do I write in OpenMP? Do I write in OpenACC? Do I write in OpenCL? Do I write in SYCL? Do I write in FUBAR, XYZ, whatever?
I wanted to experiment with this just myself like 6 months ago, and I couldn't decide what to use, and so I just gave up.
Mm-hmm. And that's what people do. People need to get work done. And the problem is, as the architectures start to come out, that's the time where you need to experiment with new algorithms, new ways of writing code. 10 years later, it's too late. Mm-hmm. You don't have time to experiment. You don't have time to influence the architecture, the vendors. It's already given to you, and it may be terrible. It may be not helpful for what you need to do. And so especially people who do supercomputing, they need the ability to be early adopters so that they can influence, or at least beg and plead. And so that's really what Kokkos is. Kokkos is a common interface to a lot of these shared memory programming models.
Okay.
And so it helped us become early adopters of them so that we could write code to a single programming model and it would work on NVIDIA GPUs, it works on AMD GPUs, it works on Intel whatevers or any kind of architecture you want that has threads in it.
So are you still involved in Kokkos project?
I'm a little bit tangentially because a lot of my work with C++ standard proposals, the collaborators like Christian Trott are people who are in charge of Kokkos, who work on Kokkos.
Okay. So I could download Kokkos. What is it? Is it, I mean, like from a programmer perspective, is it just a library that I use that abstracts these programming models away for me?
Yes, that's right. And
Okay.
so it presents a common interface so that you can write parallel loops, parallel for loops, reductions, scans, parallel patterns, and also multidimensional array data structures.
So that, but then I need OpenCL or whatever installed also for it to talk to?
That's right. So it's a configure time choice. So at
Okay.
configure time in Kokkos, you decide I'm going to use OpenMP, and
Okay.
then Kokkos can use multiple programming models, but you specify when you're writing code, I want to target this to the OpenMP backend, or I want to target it to the CUDA backend.
I see.
Okay.
Now, does it have a stable ABI?
No, it does not. It does not aim for that. Although that has become, occasionally the question will come up, oh, I'm writing Python and I want to use Kokkos.
Right.
And Kokkos is C++. It relies on passing in lambdas and functors and compile time things. It's very compile timey. And it has to be optimized because OpenMP is not just a set of pragmas. It's like shifting gears in your compiler and you engage a whole nother compiler mode.
Right.
Like sometimes when you have OpenMP on, the compiler's doing different things to loops, like different chunks of optimizer kick in.
Right.
And so the compiler needs to see the loop. It needs transparency through the inlining. I mean, that's historically been, you kind of hope that the compiler will inline things because that's how Kokkos works.
Okay.
And so ABI is not a thing with Kokkos, but if you're a Python programmer or a Fortran programmer, then maybe you wish that you could use Kokkos or you want to be compatible with Kokkos. And there the story is a little bit harder because it's a C++ thing. I mean, Kokkos, in using something like OpenMP, usually vendors, when they provide OpenMP runtimes, the OpenMP runtimes are compatible across their different languages. And so if you have C code and C++ code and Fortran code and they use OpenMP, they generally use the same OpenMP runtime.
Okay.
And so you can compatibly call across languages. And OpenMP won't like spawn extra threads that fight each other for the system's resources. It'll use a single thread pool.
That's handy. Yeah.
And so Kokkos will just take advantage of that, but Kokkos doesn't have its own thread pool. So it does as a backend, but sorry, go ahead.
No, it's sorry for interrupting. If I were to write code and say, okay, I'm using Kokkos right now, I'm targeting OpenMP, but then you're like, no, wait, I need to pivot to, CUDA. How difficult is that?
Just like a switch?
You change the template parameter.
Okay.
The template argument.
Oh, okay.
Nice.
So you could then, you're saying, if I'm hearing this right, I could actually write code that targets CUDA, OpenMP, whatever, all in one project.
That was the explicit goal of Kokkos, was a single code base that can target multiple backends.
Okay.
And the reason for that is we didn't have, Department of Energy lacks the resources to optimize code for n different backends. So there's a huge code base that needs thread parallelization. Maybe it doesn't have to go at 100% flat out on every architecture, but it needs to not be slow.
Right.
That's really the goal. And if you need to optimize one particular thing really hard, yeah, you write CUDA or whatever, but you don't have to do that for every single thing. And the thing is, as parallelism increases on node, the serial bottlenecks start to matter more and more and more. And so you have to start writing everything and thinking thread parallel all the time.
Right.
Okay. So you're now involved in the standards committee over the past 5 years. What sorts of projects are you working on? What sorts of papers are you working on? How do they relate to your history with these linear algebra libraries?
Thank you. Yeah, a lot of my history in linear algebra libraries was making them generic to support, for example, different element types, so different kinds of values in the matrix or vector. And that actually mattered for us. We had users who had scalar types, C++ types that could support automatic differentiation automatically. So they would just automatically compute derivatives. Or there were types where instead of computing on one thing at a time, you were actually solving n different problems at a time, like an ensemble of problems. And so you would propagate this ensemble of values as a single value, and it would have all the overloaded operators and behave like double or float. Or there were types where you could embed like solving a tiny partial differential equation inside, where people were solving stochastic partial differential equations to do uncertainty quantification. They were trying to figure out the probability of something terrible happening by running a lot of different problems that are slightly different from each other and looking for worst cases. And so people were pushing all kinds of crazy element types through my library. And so I learned a lot about, well, how do I write a generic library? How do I support generic element types? These are things that people want to do. People want to put quaternions in matrix multiply. People want to put complex numbers in there. People want to mix precisions. People want to have matrices of float, but they want to accumulate in doubles so they get better accuracy. Those are all things that people want to do. And so one of the proposals I've been spending a lot of time on recently is P1673, which is a C++ wrapper for the BLAS, for the basic linear algebra subroutines. And that I took the lessons learned from generic linear algebra and I applied them. And I wrote a companion paper to that, 1674, and it talks about my experience of given the basic linear algebra subroutines, which is a C or Fortran library. If I'm writing C++, what do I need to do to that Fortran library so that I can use it from C++ in an idiomatic C way? How do I make the lowest level possible, but still idiomatic C++ library out of something that was written for Fortran 77 code or Fortran 4 code? And if you look at some of the older routines.
Fortran 4?
Yeah,
that's
so that
really old, right?
Oh, there was a lot of Fortran 4 from the people were still writing Fortran 4 in the 80s.
Okay.
But yeah, so they if you're not familiar with the history of the basic linear algebra subroutines, people might be familiar with Jack Dongarra, the recent Turing Award winner. And the BLAS was his effort at separating out the parts of linear algebra that a vendor could optimize from the parts of linear algebra that a mathematician should write.
Okay.
And so the point of the BLAS was, I work at a company that makes hardware, and I don't really know how to do a matrix factorization. But I know that I can do plus and times, and I know my high school algebra. And if somebody explains to me, oh, this is how you do matrix multiply, I can implement it, and I can make it go fast because I know the architecture. And if I'm the mathematician, what I can do is I can rewrite my algorithms to use these BLAS routines that the vendor knows how to optimize. And if I do that, I can make my math go fast, as long as I spend most of my time in the vendor provided routines.
Okay.
And part of that was an insight about how the importance of memory locality. And that importance has only increased over time, where arithmetic is practically free on a computer. Memory bandwidth costs you money, hardware essentially, but memory latency is physics. You just can't get around it. And so the way that you make your code go fast, physics. I credit that saying to my co-advisor, Kathy Yellick, who was a Berkeley professor who was in charge of the supercomputing center in Berkeley. She said that arithmetic was free, bandwidth is money, latency is physics. And
what's her Admiral Grace
Hopper.
right?
Yes.
She was known for carrying around, this is a nanosecond or whatever it was.
Yes.
Do you know what we're talking about, Rob?
I
It was
do
like a
not.
piece of metal or something that she would bring to
Network cable.
lectures.
Yeah.
This is how far light travels in a nanosecond. Was it a nanosecond?
Yeah, something like that. Yeah. Yeah.
So that you could like actually visualize physics matter.
Yeah. And for data centers, like if I'm programming multiple nodes, I mean, a lot of the latency comes from hardware and software needing to interpret my message. But yeah, the length of a cable matters. Like the reason the Cray vector supercomputers had their funny layout with the sofa around the central core, like the central core was laid out because of latency concerns for memory. Like it's designed that way on purpose.
Any high frequency trader will tell you how important it is to be co-located at the exchange these days.
Very important. Yeah. So the way that people have been writing linear algebra for the past 30 or more years has been focused around memory locality and in carving out, designing the algorithm so that it can spend most of its time in BLAS algorithms that have the most memory reuse potential. And so that's really what this proposal is about. It's just the C++ version of that. And that being idiomatic C++, that implies more genericity, supporting more types, also supporting parallelism through execution policy overloads. And the way in C++ that we express a matrix or vector, we didn't want to write like a matrix class hierarchy. That's not something we wanted to do. We wanted to be as low level as possible. And so the analog of iterator for a matrix is MDspan. So that's the proposal P0009. And that's how you view a matrix. And MDspan also has genericity on the layout of data and how you access the data. And so you can use MDspan, for example, to access, we've written accessors for partition global address space. So memory that lives on another node that you have to call a special function to get to. You can use MDspan to express that for NVSHMEM for our NVIDIA hardware. NVSHMEM is your how you can, in a shared memory kind of way, you can get to memory on remote GPUs.
So back to the BLAS. So basically, every vendor already has some implementation of the C version of this, right? And you said this would be like, so are you expecting that the C++ proposal, if it's accepted, would literally be a wrapper around the existing implementations or a fresh implementation in C++? Like, I'm just curious.
So the reference implementation that we have, what we expect is if you can call the C BLAS, you will. Otherwise, you'll write generic C++ code.
Okay.
And so there may be a bit of a performance, I don't want to call it a performance cliff, but yeah, if your element types or layouts are not supported by the C BLAS, then we have to write C++. But that in itself is an opportunity for vendors to optimize. And some vendors do optimize things like mixed precision or interesting element types. So it's really, sorry, go ahead.
Sorry. No, go ahead, please.
Yeah, I was just saying it's kind of an opportunity for vendors to say, oh yeah, well, we have this cool new feature that says this like short floating point type or this extended precision decimal floating point type or this crazy element type. We optimize that, or we optimize this new interesting, recursive matrix layout that improves cache locality. And so the C++ interface is like the users just call that, and it's generic, but then the vendors can do optimizations underneath however they like.
It kind of seems like the exact kind of scenario that has always kept the Intel C++ compiler around, is people say, well, I know that I need this optimized whatever feature that Intel's compiler supports.
It's a little bit like that, yeah.
I can just imagine Intel, for example, saying, yes, our BLAS C++ interface is going to be the best or whatever, because they want to highlight their hardware.
Although you can use you can use the Intel BLAS without the Intel compiler. And so there may be interesting questions for vendors about whether they want their implementation to support switching BLAS backends. I mean, that could be a thing that an implementation could do.
Right.
Even at runtime, they could load a different DLL and swap in different functions. You know, that there are a lot of options for implementations.
So is this proposal related to the linear algebra proposals that we saw come out of the graphics proposal from Guy Davidson a couple years ago?
No, it's
okay.
So we actually have a joint paper in which we describe the relationship between the two proposals, which is we are not in competition.
Okay.
Okay.
So their proposal serves a different audience, I would say. So the proposal in question is P1385.
Okay.
And the design is matrix classes and overloaded operators, vector classes, you know, times and plus on matrices and vectors.
Right.
And so those are things that graphics people want and need to do, and they like doing it that way. We chose a different approach for a few different reasons. First of all, we didn't want to try to figure out, like what's the element type of adding two matrices. So let's say I have a matrix of double and a matrix of complex float. What's the element type of their sum? It should be complex double.
I would think complex double would be my guess, but you know, like sometimes I'm like, I'm not a math person.
Well, it's worse than that. In C++, if you try to plus a float and if you use operator plus on a double and a complex float, you get a compiler error.
Oh, really?
Yes, okay. It's very exciting.
I've spent very little time with standard complex.
Yeah, it's maybe perhaps for the better. It's not bad, but it's people naively think that, oh yeah, it works just like float, and then they try to write code and it's different.
I've only used it for Mandelbrot rendering because that's all complex numbers.
So when you have a matrix operator plus, you have to decide what the return type of the element type should be. You also have to allocate. And so now you start to get into the business of storage and allocation. And what if I don't just want to do new? What if I want to allocate on a GPU or something? And now you've conflated the issues of allocation and storage and representation and the actual functions. And so what we tried, I'm not saying that that's bad, but I think for the graphics use case, a lot of linear algebra problems for graphics are small. They're 4x4 or 3x3.
Right.
And there, a lot of people who are doing graphics, maybe they want operator overloading. They don't want to call a function with a long name. So I feel like that's perhaps could be a different use case. I don't want to say that there are many users who are happy, like the kind of MATLAB user who has medium-sized matrices and they're not really concerned about this problem. They want A plus B to return a matrix and they're happy with that. That's not really the world in which I lived. I was the kind of person who was implementing MATLAB, not the person who was using MATLAB generally. Although I've used MATLAB, but yeah.
Right. Okay.
There's a fun story about the history of MATLAB, which is that Cleve Moeller was trying to teach students linear algebra, and they were all programming in Fortran, and the students spent most of their time trying to get Fortran to compile, and Cleve didn't like that very much, and so he wrote a wrapper around Fortran, and that's what MATLAB is. At least the beginning of it. But anyway, please continue.
Interesting, actually.
I was going to say, I was looking at the P1673 paper you have, and you're currently on the 7th revision, which just went up like 10 days ago. How's this moving along? Are you getting good feedback in the committee meetings?
We are. Yeah, we just actually this morning we had a review of the paper in LAWG in the Library Evolution Working Group, and we had a lot of great feedback. It's probably going to see more LAWG review before it's done. And some people are concerned about the length and the amount of wording review to do, and whether perhaps it would be better to spin off as a TS rather than an IS. That's not something that I've wanted to do because it's not clear that that would save any work. But you know, there is a lot of discussion about the length of the paper and the number of functions in it. I don't want to give up the functions, especially the BLAS 2 and 3 ones. Those are really critical. Like, you really need all of those functions to do basic linear algebra. And it's a lot more than plus and times.
And you said there is a reference implementation. Did I hear that right?
Yes. So you can find the reference implementation. It's linked off of Kokkos's GitHub.
Okay.
So it's GitHub. I'll type it in the chat.
Make sure we get that in. Okay.
Yeah. And there are
standard BLAS. Okay.
Yeah, and there are reference implementations also of MDspan, which is P0009, and MDarray, which is P1684.
Yeah, I think we talked to Daisy Hoemmen a few months back about MDspan. Yeah.
Yeah, so the MDspan repository has the latest reference implementation of MDarray now.
So for listeners who are interested in trying these reference implementations, do you have Conan VC package? Is it fetch contentable? Like, is it easy to get and use in your library?
It's a little more than that. It's typical CMake and a little bit of handwork, so it's not very beautifully packaged. But the goal is more of that.
Okay.
But it's not, in terms of build system, it's not hideously complicated.
Okay. Just curious, like, you know, so our listeners know what they're getting themselves into.
For sure.
You didn't say you have to run a bunch of custom shell scripts, so I think you're.
No. It's CMake. It's all CMake.
Okay. So it looks like MDspan and MDarray are probably likely to get accepted soon. Is that
MDspan is in the middle of wording review, and we're hoping C++ 23. MDarray is still undergoing design changes in design review, so it almost certainly will not make 23.
Now, if I understand MDspan right, I can say I've got a flat array or a vector or whatever, and say, I want now you to give me a view of this as if it were a fourth dimensional array, whatever, with this layout and access patterns and such.
Yes, that's right.
Okay. So then, dumb question, what is the need for MDarray then?
So the point of MDarray is convenience, so that you don't have to do what you just described, create a vector and then create an MDspan to view it. You can just create an MDarray and it does that for you.
Okay. And
so another point is, if you have very small arrays, so arrays of small types that have compile time dimensions, you know, your 3x3, 3x4 case, MDarray doesn't need to store a pointer. So MDspan is a view, and it stores a pointer and possibly any extents that are not known at compile time. So MDspan will always store a pointer. And you can have types that are small enough that the whole thing will fit in 64 bits. Or, you know, maybe it doesn't take much more than that. And so MDarray can optimize for those use cases where you have very small objects that you would maybe use an array, std array, to store. And so MDarray can use a std array to store things.
I don't have the math background for this at all, but I just found myself wondering, like, is there a use case, and I'm kind of visualizing like C-style arrays, where you could say, I want one that's, I know it's 5 dimensions, it's vector backed, but I'm only going to tell you the length of the first 4 dimensions, and the 5th dimension can grow dynamically as we add more data to it or something like that. I mean, not that you have dynamically growing arrays in C, but if you declared a C-style array, you only have to declare, you don't have to declare the size of the last dimension, because that is just another point, that's just an index offset at the end. So just a random thought, like, is there a use case for something like that? Does that exist? Is that a math thing? I'm just talking.
No, users sometimes want to do that. So for example, users may have tensor data that can be organized in a time series, and as time elapses, more data sets are added to their collection, and they may want to represent that as a single tensor. Mathematicians sometimes grump at me if I say the word tensor, but they want to represent that as a single multidimensional array and just pack on to the end.
Right. Yeah, okay.
That's a thing that people want. That's not in our design.
Right. Well, it just made me wonder, is MD vector on the horizon or something like that instead of MDarray at some point? Like, if that would be a use case.
We haven't thought about that. We've excluded that from the design because you have to think very carefully about compile time versus runtime extents. So the design of MDspan and MDarray revolves around this extents object, and it mixes compile time sizes and runtime sizes in the type. So just like span, STD span has dynamic extent or a compile time extent, extents is the generalization of that. And because you can mix arbitrary compile time and runtime extents, if you were to design an MD vector around that, suddenly it gets complicated. How do you know which extents you can grow and which you can't? And it gets messy. And so we didn't try to tackle that problem. I think that's a hard interface problem.
Yeah, that's fair. Like I said, I had no idea if there's even a use case for it.
But like the Python, people who do Python data analysis with pandas and whatnot, they want to do things like that. And I think the way to handle that would be the growing would happen in the Python world. And if you wanted to call into C++, you'd make an MDspan statically, call the function that you want to call in C++, and then go back to the Python world and grow it as you like.
So do MDspan and span and array and MDarray play nicely with each other? Like if I say, well, I've just got a Ritter stood span, is it like convertible to an MDspan with one dimension?
Yes, there are those kinds of constructors. And the history is funny. The MDarray proposal has a long history. The first paper was 2014.
Oh, wow.
And span was actually split off from MDspan. That's the origin. Where people wanted a simpler vocabulary type, where pointer was actually like T star.
Right.
And with MDspan, the pointer type can be more general. And so for a vocabulary type, people wanted span to be a separate thing. But yeah, the two are interconvertible. I mean, array, it's very annoying that the dynamic version of array is called vector. The name is unfortunate. And so MDarray can have a mix of compile time and runtime extents. So it's different than std array.
Right.
But the naming is difficult, but we don't know what else we could call it. It's an array. That's what it is. Sorry.
Yeah.
All right. Well, Mark, we're going to put links to all these papers and the reference library implementations in the show notes. Is there anything else you want to plug or let our listeners know about before we let you go today?
Well, I just wanted to thank you for giving me the opportunity to speak and thank the listeners for listening. And I welcome feedback on any of these proposals, especially stdbls or MDarray are more in the design review stages right now. Those are we especially welcome feedback on those, but also on MDspan. If you find a bug in the spec, now's the time to look. So I welcome any feedback you may have.
All right. Thanks so much for coming on today.
Thank you.
Thank you.